Hi class, welcome back to Electromagnetics. So we've gone through a couple of lectures of some pretty involved calculus and differential equations, trying to solve Maxwell's equations simultaneously, which we've arrived at a pretty massive general solution. So now we want to try to drill down on this a little bit and see if we can't get a more concise solution for a uniform plane wave. Thought for the day. Comes from Ecclesiastes 7:8. I think this is pretty applicable considering where we are in our examination of this. The end of a matter is better than its beginning, and patience is better than pride. So I think that this nugget of wisdom here is just saying that sometimes the beginning can be tough. It can be hard to have faith. It can be hard to keep going and have endurance and have patience. But I think as you start on an endeavor, much like getting your degree or something like that, that as you come to the end of it, it's usually much better than the beginning. You can start to see the results of your labor and the fruits of your labor. And so it's better to be patient than to have pride to talk about at the beginning what all you're going to do. So I thought that's pretty applicable today as we're wrapping up the uniform plane wave discussion. So we're in the fifth mini lecture of this part 4. Again, I want to come up with a general, concise equation or approach to uniform plane waves. So as we ended up before, we were talking about these trigonometric terms and their arguments, cosine omega t minus beta z. And so we want to take a little closer look at that, make sure we understand it. So let's look at 3 cases of this then with just this term. If we take t equal to 0 and plug that in, we'll just get the cosine of negative beta z, which is also equal to cosine of beta z because this is an even function. If we put in a time of pi over 4 omega, kind of making the math easy for us here, we see that we get pretty much the same equation but with this pi over 4 term. And then for a third point of reference, we'll let t equal to pi over 2 omega, and so we see the time is increasing as we go down or advancing. So in this case we will get the sine of beta z. So we want to take these 3 reference points now and we want to plot them on the z-axis, on the same axis, so we can see if we can get some understanding of what's going on here. So here we have all 3 equations on the z-axis. So this first curve, let's see at t equals 0, that's this curve here. Hold on, let me get my pointer. So we have this first term here, and so this is the first wave at t equals 0, and then as we let time advance to the next spot, it's this one here, and then if we let time keep advancing, so you can see these peaks kind of keep moving down in the plus z direction. So it should be evident that each of these graphs is identical in size and shape, but merely shifted then along the z-axis. So it's going in the plus z direction. So in fact, as time increases, it gives us the appearance then that the wave is shifting, or what the term we use, it's traveling in the plus z direction. So as time advances, this wave seems to be moving in the plus z direction to the right. So much so that we can even calculate the velocity in which this wave appears to be traveling. It comes out to be what we might expect, the speed of light, but we can calculate it as follows. So we take the difference in position divided by the difference in time corresponding to these positions. So as we do this math, we see that we get omega over beta. Well, we know from definition, applying our definitions for these, we get 1 over the square root of the permittivity times the permeability. Plug in the values that we defined for that early on, maybe 2 or 3 lectures ago. We come up with 3 times 10 to the 8 meters per second, which this is the accepted speed of light that we are familiar with and hopefully have seen already in physics class. So if we do the same thing, but now change the sign from a negative to a positive, we can plug in these values for t again. This time we can see that this peak is now moving to the left, or in the negative z direction, as seen above. So now if we return to our general equation that we had for the electric field, we see we have these terms in here with the negatives and the positives in the argument. So with our new understanding of the propagating waves, we now notice something important about our equation. Since we've defined the infinite current as the only source, we should only have waves propagating away from this current sheet, right? Not towards it. Hopefully this physically makes sense. So if we have this current sheet in the middle, the wave should be propagating away, not toward it. So since we only have propagation in the plus z direction, we're only looking at the plus z direction, we now know that this means mathematically that the trig functions above with the plus sign in the argument must be equal to 0. That is, we can't have propagation in the negative z direction back towards the current sheet. So these two terms have to equal 0. So with this in mind, we can now set those equal to 0, which will now let us be able to solve for this c value and this d value. So again, solving for c and d in the above equations, we see that d has got to equal to 0. That's the only way that this is equal to 0 for all t and z. And again, taking the other side of the equation, we see that the only way that this could equal to 0 would be if c is equal to eta naught times the current density over 2. So now we've solved for c and d. This allows us then to write our expression for the electric and magnetic fields in as follows. For the conditions when we're on the plus z side of the current sheet, our electric field, magnetic field, can be expressed as this. So this is our expression again when we're on the plus z-axis. But now we can also do the same thing for the negative z-axis, that is on the left-hand side of the current sheet. And so we have this expression here for when z is less than 0. So we're almost done, just a little bit more. We can now combine these two sets of equations and make use of vector notation and operators to write one single solution then as follows. So for our electric field and for our magnetic field, we have this. And so you notice these are bold now because we are using our unit vectors here to tell us the direction. And again, I don't know if you're familiar with this notation. So for z greater than 0, we use the top sign, and for z less than 0, we use the bottom sign of the plus sign. So this takes care of whether we're on the right-hand side or the left-hand side of the current sheet. Same thing here for these signs here. So this is the general solution then for the electromagnetic wave that is generated from this infinite current sheet in the xy plane, where the current density then is defined, as we did here a couple of lectures ago, as just this constant times this trig generator cosine omega t in the x direction. So again, if we look at this, the current sheet here in the middle in the xy plane, you can see that you'll have on the plus c side, this wave will look like it's propagating away from the current sheet. And again, on the left-hand side, same thing. It's if you look at the peaks, they're moving away from the current sheet. And so our equation takes that into account, our general equation for this. So now that we have a solution for our electromagnetic wave, we now need to look at some useful characteristics of electromagnetic waves that we kind of defined as we were going along here, but we want to summarize them here. The first is we have a phase constant, so that's our beta term, and so that's omega times the permittivity and permeability square root. And so for fixed time, this is how the phase changes. We have our phase velocity. Again, this is how the peaks appear to be moving down the axis, and so that's omega over beta, and we've already calculated that. And so for free space, it's 3 × 10⁸ meters per second. We have our wavelength, and so this is the distance for phase to change in 2 pi, so from one peak to the next. And then we have frequency, what we're more probably used to thinking of in terms of hertz, and so this will be our phase velocity, this term up here divided by lambda. And finally, we're going to have what we're going to call our intrinsic Z, which are our intrinsic impedance, and we're going to look at this in more detail later. But this is the ratio of our electric field to the corresponding magnetic field that's generated here. And so this is equal to, we define this as eta naught. And so this is the permeability divided by the permittivity square root. So if we plug those numbers in, it turns out that it's 120 pi omega, or if you want to force a number on that, it's 377 ohms. And so in free space, this kind of gives a relationship with the magnitude of our magnetic field that's generated by this electric field. So if we examine the cross product then of the perpendicular wave, E, our electric field, and our magnetic field in the XY planes respectively, so we can take this cross product, and so it'll be this EX-AX cross with this HY-AY. Should be non-zero because as we take this cross product, those are orthogonal to each other. We come up with this new term, plus or minus the current density magnitude squared over 4 cosine squared with this argument in the z direction. And again, this is going both directions away from the current sheet. So the result then is a new vector in the direction of the propagation of z. This cross product will be utilized again in the very near future, in fact in the next lecture, and we'll see that this does have some pretty major significance for us as we continue to look at this. So let us now consider an infinite current carrying sheet in the XY plane with the current density defined then as this. So this is just some arbitrary function of t. So before we had a cosine omega t, but we could just say it's minus js, just any function of t. So it doesn't have to be a sine wave, it could be a square wave, triangular wave, who knows what. It could be anything we want. So if we have this case, the solution then for the electromagnetic field generated by this current then is then arbitrarily defined as the intrinsic impedance over 2 times the original function for the current density with this new argument. Instead of t, it's then t minus or plus z, the position over the phase velocity ax. And again, this plus or minus is, we pick which one depending on if we're moving in the plus x plus z direction or the minus z direction. Likewise, the magnetic field is plus or minus 1/2 times this same current density with this new argument in the y direction.